Welcome to lecture 5 on risk management and insurance. In this lecture, we will first show how strong the effect of a change in yield on the bond price is. And after that, we move on to forward contracts, which are a different topic. Remember, the bond price is given by the present value of all future cash flows. Those cash flows run from year 1 up to year big T when the bond expires. They involve the interest payments, and when the bond expires, the investor also gets back the face value of the bond. So the price or value of a bond depends negatively on the yield. We have here a negative power. And I can now use here the function notation. So the bond price is a negative function of yield. For the functional operator, I'm using here a B for obvious reasons. We deal with bonds, but that's naturally arbitrary. Usually for functions in high school math, we use a small f. That the functional operator is a small f. But here I will use a B. Before, actually, I even did not mention that it's a function. So here we just set the bond price in equation 24. We just said the bond price is a present value of all future cash flows. But now here we highlight that the bond price is a negative function of future cash flows. So here on the lower axis, I have the yield of the bond. On the upper axis, I have the price of the bond. The bond price is a negative function of yield. It's actually a nonlinear function. It's downward sloping here in a nonlinear way. Here I have again written down the function. It's a nonlinear function and the function is convex. Now what I would like to do, I would like to calculate here what is the change in the price of the bond if the yield changes. And I would like to do it at this point here. So the correct answer is naturally to move along this nonlinear function, but we will do an approximation. We will do a linear approximation. We will move along this linear line, which is just a tangent at this point. That's very often done in finance. If you have nonlinear functions, you make a linear approximation, and that's good enough if the changes are not too big. So let's look at an increase in yield. This will reduce the price of the bond. And we will move along the linear line. The correct reduction in the price of the bond is a little bit less. So it will be here. So we make here an error. But this error will be small if we only deal with small changes in yield. So if the changes in yield are small, then the error here will get smaller and smaller. So I have here the change in the bond price. Here I have the change in yield. And this is a rectangular triangle. So if you divide the change in the bond price by the change in yield, you get the tangent of this angle down here to the linear line. That's just from the geometry. The tangent of this angle is also here, it's just this negative rate of change. That's equal to the first derivative of the straight line. So if you divide delta b divided by delta y, you get here the first derivative of the straight line. And if you do it the other way around, if you have the first derivative here and you multiply by dy, then you get dB, delta B. So delta B divided by delta y gives you the tangent of the angle, the first derivative, but then you actually can change the formula. Okay, solve it differently. So you have the first derivative times delta y gives you delta B. So that's what I have here on the next page. But let's again rid of that. So first derivative times delta y gives you an approximation of delta B. So what we need is this first derivative. And we can calculate it going back to the present value formula 27. So here you have the function, the bond price depends on yield. Now make the derivative with regard to y. If you have never done a derivative with a summation sign, just write it out. Just write out this summation, all those items up to from time 1 up to big T. So then do the derivative, and in the end again use the summation sign, collect the term, and again use the summation sign. The only thing you have to be careful here, here's a y, we do the derivative with regard to yield. It's up here the power of E. And so you have to take the derivative of the power. You get here a minus t. That's because of the chain rule. So don't forget the chain rule here. So that's what we have here. This minus t comes from the chain rule. And that's the derivative. If you again use summations, then in the end. Now, if you use equation 25, ETC gives you just BD. That was the definition here of duration. You can factor out the B here, and then you can multiply on both sides by B. So BD just gives you the sum ECT here. So just multiply here on both sides with B, and then BD, okay, the sum of those three terms here. So BD is a sum of those three terms, and then don't forget the minus sign here. So I can plug in minus BD here for this first derivative. That's what I have done here. So here have the change in yield, and this gives you an approximation, this equation here, for the change in the bond price. So here it's done in dollar terms, and if you would like to know it in percent, then just divide both sides by B. So you have here now the percentage change here, the B drops out. So an increase in yield, in the market yield, reduces the price of an existing bond. It's a negative effect. Okay, we have here a minus sign. And the effect is strong if the bond has a long duration. Remember, the duration is not equal to the maturity of a bond. So a 10-year bond may have a duration only of 7 years. It's the average time when you receive money, and as interest payments you get actually earlier. You don't have to wait for 10 years. But the duration and maturities are naturally related. So generally, if a bond has a longer maturity, it probably also has a longer duration. But what really matters is the duration. Now you may have noticed that by following a linear line, by following the tangent, what we have actually done is a first order Taylor series expansion. So moving along this linear line amounts to doing a first order Taylor series expansion. And so when the yield increases and the bond price falls, we have here this error. Now, when you do a second order expansion, you can reduce this error here. So actually this tangent here also will become slightly curved. And the error here will shrink. So let's now do, so we have here the first order Taylor series expansion. Here, first derivative times delta y. That term is still here from the first order. First derivative times delta y. But now I'm also including a second order term, which depends on the second derivative. So that's basically all you have to know from calculus in this class. You should be acquainted to Taylor series expansions. I also will use it again later. And you should actually know the chain rule of calculus. This one also I will use repeatedly. Now, the second order derivative here measures the curvature of the function. So convexity is defined as a second order derivative divided by b. Or if you multiply b by convexity, then you have here the second order derivative. And because the curve is convex, this second order derivative is positive. Remember here, it's a nonlinear relationship, but it's convex. So the second order derivative is positive. This will be positive, the second order derivative, which naturally means the C is positive because the bond price is anyway positive. So we can plug in this here. Let's take this, plug it in here. And then also plug in from before for the first order derivative. Remember, the first order derivative was just it was minus BD. So take that again here, use it here, and use this here. And we get now here this approximation of the bond price, which involves a smaller error because it's based on second order Taylor series. And if you want to know it in percent, then again divide both sides by B, and then you get the percentage change in the bond price, and the B cancels out. So an increase in yield reduces the bond price strongly if it has a long duration. If T is a long duration of the bond, then we have this negative effect that's strong. And the convexity, if the convexity is low, so if that's a small term here. You see the convexity actually offsets this first effect. The convexity is positive. We have a convex function. So here we have a positive term, here we have a negative term. So the effect is strong if the duration of the bond is long, and if this positive term here then is low, because that's offsetting the negative effect here. Now that's very important for banks and insurance companies and other financial institutions. They hold large amounts of bonds. They invest money into the bonds and then return interest on it. But when the yield on bonds increases, bond prices fall. So financial institutions, bank, insurance companies, they make losses on those bond holdings. And so they will try to estimate how sensitive are those bond holdings, the value of those bond holders, to changes in yield. Higher yield means losses for them. The bond prices will fall. And so they will calculate the duration, the convexity, and those equations here. And then they will try to immunize their bond holdings from changes in yield or the interest rates. And they do this through hedging. But this we will discuss later, okay, how the hedging is done. But it's a very important thing for financial institutions. How sensitive are their bond holdings to changes in yield? Because if the yield increases, then they make losses. Naturally, if the yield falls, then their bond will increase in value. So let's move to the second topic today, which is derivative security markets. That's a different topic. Derivatives include forwards, futures, and options. And they can be written on securities, shares and bonds, but they also can be written on commodities like wheat or oil, and also on currencies like okay, maybe the yen or the US dollars, and also on other assets. You can use derivatives for arbitrage, speculation, and hedging, and we will discuss this in this and the next lecture. So, but we will mostly then focus on hedging, because hedging is similar to insurance. Hedging reduces the risk. So let's begin with a forward contract. A forward contract is an agreement to buy or sell an asset at the future date for a given price. That price is called the delivery price. So the contract is set up today, and all what the contract says is, okay, at what, maybe you buy forward an asset, then in the contract, all what is done, it's written what the price will be in the future at which you can buy. It can also be used for selling. So you do a forward contract and you agree on the price at which you will sell that asset at a future date. Typically, this time interval may be 90 days or half a year. It would be unusual to do a forward contract for more than 1 year. You could do it possibly, okay, if you find another person who is willing to engage in this contract. So what you do with a forward contract, you lock in the price. Today you agree to buy something at the future date at some predetermined price. Naturally, you don't know what the price will be in the market at this future date. So here there is risk involved. So you obviously can use it for speculation. So you lock in the price. So at time small t here, when the contract is being written, no money changes hands. Also note that we have here changed the notation. The current time I'm now using a small t. Before I called it time zero. So we have now here a time interval big T minus a small t. Before the small t was just a zero. So the time interval was just a big T. This is actually the better notation here. So let's look what can happen when you take part in such a forward transaction. When you buy forward. So let's assume you buy oil forward. The delivery price is $40. And so the delivery will take place maybe in 90 days. So that's the delivery price K. Now, if in 90 days time, it turns out that the price of oil is $50, then that's very good for you, because you have locked in 40, you still will get it at 40. So you have here a positive payoff of 10. And if in 90 days the price of oil is even better, if it's $60, that's even better for you, now you have a positive payoff of 20, because you still get, you have locked in the price of 40 here. So now in 90 days you will pay 40, even if in 90 days then the price of oil is 60. You have locked in the price and you have this positive payoff. So for every additional dollar here in the future that the price of oil is higher, you will have an additional dollar of payoff. So we have here 45-degree lines. But naturally the market can move against you, and maybe in 90 days it turns out that the price of oil is only $30. You still have to buy it at 40. You locked in 40 and you must take delivery at 40. You cannot renounce the contract. So you pay now too much, and you have a negative payoff, minus 10. Now, if you sell forward, maybe you're an oil producer and you sell the oil forward for $40. It's $40 here. Now, so you sell forward at $40, so you must deliver the oil in 90 days at $40. Now, if in 90 days the oil is only 30, then that's very good for the seller. You still can actually sell at 40. You have locked in the price at 40. So oil price turns out to be only 30. You have here a positive payoff of 10. But then again, the market naturally may move also in the other direction. If in 90 days the price of oil is 50, and here's a seller has locked in 40, and the seller must still deliver at 40 something that now really has a value of 50, and so the seller has a negative payoff of 10. So what you do here in those graphs, you plot the payoff against that you will get at time big T here. So that's the price of oil at time big T when the contract expires and when delivery takes place. This price will naturally, this price you don't know in advance, so this shows the situation. So this graph shows the situations that will happen. Okay, if you have different prices here in the future. It shows the situations for different futures prices, and those prices you actually don't know ahead. Okay, so that's a forward contract. It's very important. It's actually done very often in financial markets. It's done for commodities. It's done for bonds. It's also done for shares, and it's also done for currencies. Let's make an example. Let's have a mining company in South Africa. It has delivered some ore to America, and they will be paid in 90 days $1 million. So the mining company has now exchange risk. It does not know what the exchange rate will be in 90 days for the US dollar against the rand. So what the mining company can do, it can sell those dollars forward at a forward exchange rate. And then it knows exactly what it gets. So it can lock in this exchange rate, this forward exchange rate, and then it no longer has any exchange risk. So it can hedge this risk. And that's in international trade, that's that's commonly done, because a mining company should not speculate. As a mining company knows, okay, in the future they will get those dollars, but they don't know the exchange rate here in 90 days time. And so actually, because they can sell those dollars already today at the forward exchange rate, they can lock in the exchange rate, and then they know exactly what they get. They get rid of the risk. And they quite often, almost usually, they will do it because really mining companies are actually not speculators in foreign exchange markets. So this hedging of the exchange rate is very important in international trade. Here another interesting example for a wheat farmer. Now a wheat farmer maybe takes 6 months to grow the wheat, but the wheat farmer during the growing season does not know what the wheat price will be in 6 months' time at harvest time. So the wheat farmer may sell the wheat forward before harvest and lock in the price of wheat. Then the wheat farmer has gotten rid of the price risk. That's again hedging. But here actually this is not so innocuous. That's actually quite dangerous because it only hedges the price risk and it does not hedge the production risk. The wheat farmer has also the production risk. Let's assume there is a drought or there is a big storm and the wheat is destroyed. And the farmer has sold the wheat forward to hedge the price risk. Now the farmer still has to deliver the wheat at harvest time, even if the farmer does not have the wheat. So the farmer has now to buy wheat in the open market, and if the price is very high at that time, then the farmer make a big loss. So wheat farmers sometimes will actually sell wheat forward to get rid of the price risk, but then they still have the production risk, and that actually can be considerable. So it's better for a farmer than to buy a put option to sell the wheat. And we will discuss these put options, we will discuss in the next lecture. Okay, this finishes the lecture for today. Thank you.